All right, so let us start our lecture today. So today we're going to learn about PD, all right, which is question 2 in the midterm. All right, so in order to solve PDs, you have to know how to solve a boundary value problem because the method is the same. You have to extend the method of solving boundary value problems to PDs. All right. So let us try to solve this kind of. So first, PDs. This is time-dependent problem. All right. So let us try to solve the problem that we have in our exam. All right. So you have dt of v minus y squared v second minus y v prime is 0. In this case, y is from 1 to e, and t is from 0 to infinity. All right? At 0, you have gy, and v at t of 1 and v of t at 0 will be 0. This is for y in 1 to e, and this is for t from 0 to infinity. So this is the problem that we have in exam. The function g will be discussed later. But the first thing I want to emphasize for you is the boundary condition. All right? Boundary condition. So in this problem, we have two variables. In this problem, we have two variables. All right. So in this problem, you have two variables, t and y. T and y. So for each variable, we need one boundary condition, one type of boundary condition. All right. So in this problem, you have two variables, y and t. All right. Which means that you have to have boundary condition for t, and you have to have boundary condition for y. All right. So you need boundary condition for t, and you also need boundary condition for y. All right. So in this case, I consider t from 0 to infinity. In this problem, we consider t in 0 to infinity, so we need boundary condition, and t is 0, and y is in 1 to e, so you need boundary condition, and y to be 1 and y to be e. All right? So I explain again. So in this problem, v is a function of t and y, right? So v is a function of t and y, right? Because v is a function of t and y, you need boundary conditions for both t and y. All right. So which means that you need to to find the boundary condition for t and the boundary conditions for y. So now in this case, I consider t from 0 to infinity. So I need a boundary condition at these endpoints, t to be 0. All right. And because I consider y to be from 1 to e. Alright? So I'm gonna need two boundary conditions at 1 and e. Alright? So if we let me explain. So since the derivative in t is of order 1. So you have dt of v. Alright, so here let me write it in a better way. So I have dxx of v. And here I have dx of v. Alright? So since the derivative in v is of order 1, we need one boundary condition for t. T is 0. Since the derivative in x is of order 2, the x of v, we need two boundary conditions for x. X is equal to 1 and x is equal to e. Alright? Yes?
Is it partial yy or partial xx?
Partial yy. Thank you. Very good. This is partial yy. Could you say at the back of the paper, please? Alright? So, in this case, you look into this equation, you see that here you have one derivative in t, which means that you need one boundary condition for t. Alright? So you solve the equation from 0 to infinity and you need a boundary condition at 0 only. In V, you have two boundary conditions. In V, you have two boundary conditions, which means that you have to have two boundary conditions at y to be 1 and y to be e. Alright? It's clear? Questions? Now suppose that we have the following equation. Alright, so the boundary condition, for t to be 0 will be v of 0, y is gy. Alright? It's clear? So, because y is still a variable, 1 to e. So y is in 1 to e. We just put t to be 0. Alright? So in this boundary condition, you just have to fix the value of t to be 0, but y is still running. Alright, so you just have to fix one specific value for t, but you don't fix y. Alright, so in this boundary condition, you still have v of 0 and y is still a variable. So the value at t is 0, but y can be taken anywhere in 1 to e, will be a function of y. Right? It's clear? So similarly, the boundary condition for y to be 1 will be v of t1 is h of t. In this case, ht is the 0 function. So when we say about the boundary condition at y to be 1, so you have to define all of the value for the function vt1, which is a function of t. But in this case, we're going to take the 0 function. All right, so it's not a value anymore. It's going to be a function. Right? Questions? So I explain again. There's a big difference between boundary value problems on 1 dimension and boundary value problems on higher dimension. All right? So the big difference is the boundary condition. So in higher dimensions, you're going to have several variables. In this case, you have 2 variables, t and y. Right? So for each variables, you have to have boundary conditions. In this case, you need boundary condition for t, and you need boundary condition for y. All right? So in this problem, t is from 0 to infinity, so you need 1 boundary condition for t at 0, and y is from 1 to e, so you need 2 boundary condition and 1 and e. All right? So why do you need only 1 boundary condition for t? This is because you have only 1 derivative in t. All right? So if you have 2 derivatives in t, then you're going to have 2 boundary conditions for t. All right? So the derivative, again, because the derivative in x is of order 2, so you need 2 boundary conditions for x. All right? So when t is 0, you set t to be 0 in the function vty. This is going to be a function of y. This is why in the hypothesis you have gy when y is going from 1 to e. All right? Similarly, when you set y to be 1, you're going to have a function for t. But in our case, this is 0. This is the function 0, not the number 0. All right? 0 is the function 0. Is the function which is 0 everywhere. All right? Similarly, the boundary condition for y to be e will be vt e is kt, which is also the function 0. Right? Now, after you understand the boundary conditions, let us try to solve this equation. So now we only need 1 condition for t. So what is the name for this boundary condition?
Initial condition.
Initial condition, yes. So can you sign the back of the paper, please? So this is called the initial condition. Because you only need one size, all right? So if you have only 1 boundary condition for t is going from 0 to infinity, this is called initial condition, all right? So if you have 2, this is boundary condition. But if you have 1, this is initial condition. All right, so now let us try to solve the equation that we have. So we have dt minus y squared dyy of v minus y dy of v is 0. All right, so this is the equation that we try to solve. So then this is a complex situation because you have 2 variables. Okay? This is a complex situation. Since we have 2 variables, t and y. So there's a technique that we learned in the previous class to solve first order differential equation, right? Which is divide and conquer. So the technique is to split v into two variables. So this is separable techniques. This is separable techniques. We're gonna write Vty to be t of t and v of y. Alright? Alright, so this is the separable techniques. Alright? So this is separable. So I explain again. So in first order differential equation, first order differential equation, you use the so-called separable techniques, in which you split v into t, a function of t, and v, which is a function of y. All right. So this is divide and conquer. This is going back to the separable equation that we mentioned in the previous lecture. So what happens when you do this? When you do this, the following thing happens. So you're going to have dt of v, ty will be dt of tt, vy, and this is going to be t prime of t, vy. All right? So this is, so you can have a look back into the separable equation. So I have also a tutorial video on Canvas for this. So the idea of separable techniques, which works very well for first order differential equation, but it also works for partial differential equation. So the idea is that you multiply, you suppose that t, v of ty is tt multiplied with vy, all right? So you separate the two variables t and y, all right?
What if v is like a sum of the variables, like t plus y? How would you separate it into
T plus y, sorry.
Like what if you had v of ty equals like t plus y? And how would you separate it into that?
V of ty is t plus y.
Yeah,
Something like that. But it's not the solution of this equation.
Oh.
All right. So of course there's a theory after this. So I didn't explain to you the theorem, but the theorem said that okay, if you solve this equation, it has to be separable.
Okay.
All right. So this kind of thing will not happen. But of course, in this class, I don't prove any theorem. All right. All right. So this is an excellent. Can you say at the back of the paper, please? So this is an excellent question. So in this, so there will be cases in which you have t vy is something like t plus y, but this is not solution of this equation. All right. So there's a theorem saying that if you solve this equation, it's going to be separable. But I don't prove that theorem. All right. So now suppose that I can write v ty as the product of tt times vy. All right. So when I write this way, I have derivative in t of v ty will be the derivative in t of t times v. The derivative of t of this guy will be t prime times v because v is independent of t, right? Now I'm gonna try to take the second derivative, right? So I have y second dyy of v. This is gonna be y second dyy tt vy, and this is y second tt v second of y. All right. So let me explain again. I'm gonna plug this form into all of the formula that I have here, right? So I have d t of v will be this guy, y prime dyy of v will be this guy. All right. So I have y prime dyy of v will be y squared dyy of t vy, and this gives me y squared dt v second of y. Right? Now I'm gonna compute the last term. So the last term will give me y dy of v, and this gives me y dy of tt vy, and this is y tt v prime of y. All right? All right? So I explain again. So the idea of the techniques is to split v as the product of t, which is a function of t, and v, which is a function of y. So this is separable. So you separate the two variables, t and y. Now, I want to compute dt. dt will give me t prime with y. Y squared will be yy of v. This is y squared t v second of y. And y dy of v will be y tt v prime y. Alright? So I plug everything together. So dt of v minus y squared, this is equal to 0. Dyy of v minus y dy of v. So this gives me t prime t vy minus tt y squared v second of y minus tt y v prime of y. Alright? So I plug everything into the equation. I'm going to have 0 is dt of v minus y squared dy of v minus y dy of v. Alright? So this gives me t prime t vy minus tt y squared v second of y minus tt v y second of v. Alright? Right? So because everything is 0, this is the solution of the equation. Everything is 0, meaning that I can put all of this guy to the other side. And I get the following. Alright, so I'm gonna have t prime t vy is equal to tt y squared v second of y plus tt y v prime of y. Alright? So now after I plug this and z into the equation, I take the derivative. I'm going to have t prime v minus tt y squared v second minus tt y v prime. Right? So I put the other term to the left hand side. I'm going to have t prime t vy is tt y squared v second y plus tt y v prime y. Right? So in this expression, I have tt, which is the common factor. So I'm going to have tt y squared v prime second of y plus y with v prime y. Alright? It's good? Now, so in this form, tt is the common factor, so I can put tt outside, and inside this is this thing. Right? So here I have t. I have t here, and I have y here, which means that I can divide. So I'm going to have t minus t prime over t is, alright, so I divide this to the other side, and I divide this to this side, and y second v second of y plus y v prime of y dividing by vy. This is separate, right? t and y are separated. Alright? It's clear? So this is similar to the separable equation that we've learned in the first of the differential equation. Right? So the idea is exactly the same. You derive v to be the product of t and v. Right? So you plug everything inside, you're going to obtain t prime, which comes from dt, t y squared v second coming from dyy, t y v prime coming from dy. Now you group everything and you divide dt to the left hand side and vy to the right hand side, you get this equation. And this equation is separable, right? So this is a separable equation. In the sense that t is on one side and y is on the other side. All right? It's clear? So now I'm gonna put this to be minus gamma. I can put that to be gamma as well. It's the same. So if I put this to be minus gamma, I'm gonna get t prime over t is minus gamma. All right? Meaning that t prime is minus gamma t. All right, so this.
Is that a lambda or a gamma?
Lambda. Thank you.
Lambda?
Thank you. Can you just sign the back of the paper, please? So you have t prime t plus lambda t is equal to 0. All right? It's clear? All right? So I explain again. After I separate the variables, I'm gonna have t prime over t is equal to y squared v second plus y v prime over v, and this is minus lambda. All right? Because they are separate, so I can put this to be minus lambda. So I'm gonna solve this guy. So this is minus lambda, right? So which means that I want to solve this equation. So I have t prime over t is minus lambda, meaning that t prime of t is minus lambda t. So I have one equation. All right? All right. So this equation is this equation. All right? Yes?
Is lambda a constant in t?
This is a constant, right? So because why? Because here, this is a function of t. And here, this is a function of y, right? So a function of t is equal to a function of y, meaning that they have to be a constant, right?
So lambda is still like representing our eigenvalue, right?
Excellent. Very good point, right? So this is an eigenvalue. Can you sign the back of the paper, please? Right? So, right? So, I explain again. I don't have a space to write this. So, right. So t prime over t is a function of t. All right? Y squared v second plus y v prime over v is a function of y. Right? So on one hand, you have a function of t. On the other hand, you have a function of y. They are equal. Since they are equal, they have to be a constant lambda. To be a constant lambda, right? So you have a function of t, which is equal to a function of y. So there's no case that they are function, they're just constant, right? Now you're gonna solve the second equation. So you have y second v second plus y v prime over v is minus lambda. All right, so meaning that you have y plus y prime minus v. All right. So you solve the second equation on y. This is this. All right. So you have y second v second plus y v prime over v is minus lambda, which means that you have y square v second plus y v prime minus lambda v. All right. So this gives you y squared y v prime plus y v is 0. So this is an eigenvalue problem that we solved before, right? This is an eigenvalue problem. All right? It's clear? So I explain again. So because the left-hand side is equal to the right-hand side. The left-hand side is a function of t. The right-hand side is a function of y. So there have to be a constant. I call this constant minus lambda. So when I have t prime over t is minus lambda, I have t prime is minus lambda t. Meaning that I have t prime plus t plus lambda t is 0. I look into the next equation. I have v squared v second plus y v prime over v is minus lambda. So this means that v y squared v second plus y v prime is minus lambda v. So I put lambda to this side. So I have an eigenvalue problem, and lambda is an eigenvalue, right? So basically which means that you have to do the same thing that you did in the previous step to find the eigenvalue for this problem, right? Questions? So to summarize, you do Vt, y to be t, Vy. All right? So the first thing that you try to separate variables. So you define Vt to be t of t times v of y. After you do this, you're gonna get, we need to solve the eigenvalue problem. Eigenvalue problem. You have y second v second plus y v prime plus lambda v is 0, and t prime plus lambda t is 0. So this is solving for y in 1 to e, and this is solving for t in 0 to infinity. All right, so this is what you have to do. All right? I explain again. So the first thing you do is to write v as the product of t, which is a function of t, and v, which is a function of y, right? So after you do that, you take the derivative in t. In v, you're going to have derivative in t times v. You do y squared dyy, you got y squared t v second of y. You do y y of v, you got y t v prime. All right, so you plug everything into the equation, you get 0 is t prime v, which is coming from dt of v. Y squared dyy of v, this is t y squared v prime, v second. Y of v gives you t y v prime, right? After that, you group all of the t and all of the y separately, right? And then you divide both sides to t and v. You're going to have t prime over t is equal to y squared v second plus y v prime divided by v. All right? So this is a function of t, and this is a function of y. So which means that this has to be a constant, and I call this constant to be minus lambda. Right? So in this case, y and v are separate. So I'm going to have t prime over t is minus lambda. This equation gives you t prime plus lambda t is 0. The other side gives you y squared v second plus y v prime over v is minus lambda. This gives you another equation. To summarize, when you do vty to be t times v, t is a function of t and v is a function of y, you get two separate equations. One equation is an eigenvalue problem for v, in which y is from 1 to e, and another equation is the first order equation for t, which is on 0 to infinity, right? Questions? Now you have two problems. So now you have two boundary values problem, right? One for y and one for t. So what is the next step?
So yeah, exactly.
Not yet, not yet. You have to identify the boundary conditions. All right? Here you have two equations, but you don't know the boundary conditions for v and t yet. So you have to know what are the boundary conditions. All right, so we have to identify the boundary condition. Define the boundary condition for the two boundary value problem of capital T and capital V. All right. You need to identify the boundary condition for capital T and capital Y. All right. So you have what? You have V 0y is equal to gy for all y from 0 to infinity, which means that t of 0 times v of y is equal to g y for all y 0 to infinity. All right. So in this case, you have what? You have t of 0 is a constant c, and y of v of y is g over this constant c. C is some constant. All right. It's clear. So you have t times. So the first boundary condition for v is that v at 0. Of y is gy, right? So I'm going to replace v at 0y to be t at 0 times v of y to be gy. All right? Questions?
Why is y going from 0 to infinity here? I thought that was the bounds for t.
Sorry. Very good. This is from 1 to 8. Thank you. Yes. Thank you. Can you sign at the back of the paper, please? Yes. So you have v at 0, y is a function gy, right? So this v is the product of t of 0 times v of y, right? So because v is t times v, capital V, right? So this means that t at 0 is a constant c, and v of y is gy over c. It's clear? Questions? Now I have to identify the second boundary condition. The second boundary condition is what? V at t at 1 is 0, right? So this means that v at 1 is 0. So v at 1 is 0. All right? It's clear? So this is the first boundary condition. This is the second boundary condition. So the first boundary condition is the value at t is equal to 0, right? So second boundary condition is the value as at y is equal to 1. So v at t 1 is 0, which means that t of t times v1 is 0. So t is a function, all right? So you cannot say that t is 0. So if t is 0, for all t, then v is going to be 0 everywhere, right? So this means that v has to be 0. V and 1 has to be 0, right? Now you have also v at t of e to be 0. So which means that t of t times v of e is 0, which means that v of e is also 0, right? So in this problem, again, I explain again. So in this problem, because you have three boundary conditions. So for t, you have only one, which is the initial condition. This is initial condition. Initial condition. All right? Because v has only one derivative. So for t, you only need one boundary condition, which is also called the initial condition, right? Now, you have v of 0y is gy. This is the initial condition. So I'm going to replace this and that. So Vty is TTVy. So in this case, T0. So this V0y is T0Vy. And this is equal to Gy, right? Which means that T0 is a constant C, and V of y is Gy over C, right? So this is the boundary condition, and x is equal to 1, y is equal to 1. So V of T1 is 0, which means that I'm going to have to replace, again, this as at T of T times V of y. Y here is 1, so you have T of T times V of 1 is 0, which means that V of 1 is 0. Again, here I have the same as that. I have, this is boundary condition at y is equal to e, right? So I'm going to replace VTE to be T of T times capital E of E, so V has to be 0. Yes?
How do we know that T of T is equal to, like, that V of 1 is equal to 0 if, why can we assume it's that T of T?
So suppose that T of T is 0, right?
Okay.
Suppose that T of T is 0, you replace it here, the solution V will be 0. So which means that the solution of the full equation is 0. This is not possible, right? So T of T cannot be 0. So T of T cannot be 0, which means that V of 1 has to be 0. Right? So you can see it right away here, right? So if T of T is 0, this small v will be 0, which means that you have a 0 solution for our equation, which is not true, right? So finally, by separable, you obtain 2 equations. After you obtain 2 equations, you have to identify the boundary condition for the 2 equations, right? So to obtain the boundary condition for the 2 equations, you have to do all of these things. You have to plug, but this is easy because you just plug this and that back into the boundary condition of V, and you get these boundary conditions. So finally, we have 2 boundary conditions, 2 boundary value problems, right? The 2 boundary value problem. The 2 boundary value problems. You have y second, v second plus y. This is capital V. Right? Y v prime plus lambda v is 0. Y is from 1 to e, and the boundary condition is v at 0. V at 1 is y of e is 0. This is the first equation, right? The second equation will be t prime t. This is a function of y. This is a function of y. Plus lambda tt 0. And then you have what? T0 is C. And the connection with the other guy is Vy is Gy over C. Right? Right? Questions? It's clear? So the whole idea of solving PDEs is to turn the PDEs into 2 boundary value problems. That's it. 2 ODEs. All right? So in all of this work, what you have to do is to do you have to do the separable techniques, in which you suppose that the solution T is the product of a function of T and a function of V, right? So you plug these two this product into the equation, you're gonna get the first equation and the second equation. After that, you need to know what is the boundary condition that you are looking at. So when you know the boundary condition that you're looking at, then you can write the 2 boundary value problems, right? So the key idea is to change the PDE into 2 boundary value problem. And this is the idea of the separable techniques. All right? So now, let us try to solve these 2 equations. So now you have to do two steps, right? So first you have to solve for v. But in order to solve for v, you have to go through all of the three steps. All right? So in the previous class, we know that in the previous class, we know that. So what is the value that we obtained from the previous class? So we obtained that Vn of y will be sinus of n pi log y. Lambda n will be n squared pi squared. Alright? Alright? So now you have to solve the first problem, but the first problem is already solved, right? So for the first problem is an eigenvalue problem, and in the previous class, you know that this eigenvalue problem has eigenfunctions of the form sinus of n pi log y, and eigenvalues of the form n squared pi squared, right? So you want to plug this lambda n back into the second equation. So plugging n squared pi squared into the second equation. So when you plug the n squared pi squared into the second equation, you have t prime n plus n squared pi squared dt is 0. All right? So I explain again. The first equation is solved already. So for the first equation, you know that you have eigenfunctions, okay, vectors of the form sinus of n pi log y, and the eigenvalues will be n squared pi squared, right? So this is irrelevant, but the important thing is this eigenvalue, all right? So what you do is you plug this eigenvalue back into the second equation, because this is the lambda, this what that we need, right? So you don't have to, right? So in this case, lambda is n squared pi squared, right? It's good, it's clear? So I explain again. From the first equation, you found eigenfunctions that we don't care, but the lambda here is n squared pi squared. It is also the same lambda in the second equation, all right? So you plug this lambda into the second equation, you have t prime plus n squared pi squared t is 0, all right? All right, so we can continue this on Wednesday, all right?